Now in this lecture we will find out the area of the green shape using two different methods. In the drawing we have two circles and each circle is passing through the center of the other circle, and we know that the radius of each circle is equal to 5 units, and we want to find out the area of this green shape. So we'll start with the first method, but first of all I'll explain to you what is a sector. A sector is part of the area of the circle that is bounded by two radiuses and the arc that is included between those two radiuses. So this green shape is sector A or B, and the area of this sector equals to pi r squared times 60 degrees over 360 degrees, when r is the radius of this circle and 60 degrees is the angle that is between those two radiuses. So the angle must be any other angle. So actually the general formula for the area of a sector is pi r squared times the angle that is between those two radiuses over 360 degrees. In this specific case, the angle between those two radiuses is 60 degrees, so it is 60 degrees over 360 degrees, but the angle must be any other angle. Okay. Again, the area of this sector equals to pi r squared times 60 degrees over 360 degrees, when r is the radius of this circle. Okay, and then we have also the second term, that is segment. Segment is the area that is bounded by the chord and the arc that is attached to that chord. So segment AB is the shape in the green color, and it is actually the area that is bounded by chord AB and arc AB. And the area of chord AB equals to the area of sector AOB minus the area of triangle AOB. Okay, again, chord is the area that is bounded, segment is the area that is bounded by chord and by the arc that is attached to that chord. In this case, segment AB is the shape in the green color, and it is the area that is bounded by chord AB and arc AB. And the area of segment AB equals to the area of sector AOB minus the area of triangle AOB. Okay. So here we will define the center of this circle as point P, and we will define the center of this circle as point Q, and we will define the first intersection point of those two circles as point A, and we will define the second intersection point of those two circles as point B. In the next step, we'll join together points B and B by a straight line. Line segment PB is the radius of this circle because of the fact that line segment PB starts from the center of this circle, that is to say from point P, and ends at point B, that is the point on the circle itself. Therefore PB, line segment PB is the radius of this circle, that is to say it equals to 5 units, because the radius of each circle equals to 5 units. In the next step we will connect points P and Q by a straight line. Line segment QB is the radius of this circle because of the fact that line segment QB starts from point Q, that is the center of this circle, and ends at point B, that is a point of this circle itself. Therefore QB is the radius of this circle, that is to say it equals to 5 units. And we will join points A and P together by a straight line. Again, line segment AP is the radius of this circle because of the fact that it starts from the center of this circle and ends at point A, that is a point of this circle itself. Therefore it is the radius of this circle, that is to say it equals to 5 units. And we will join points A and Q by a straight line. Again, line segment AQ is the radius of this circle because of the fact that it starts from the center of this circle and ends at point A, that is a point of this circle itself. Therefore it is the radius of this circle, that is to say it equals to 5 units. So actually here we created quadrilateral APBQ. Quadrilateral APBQ is a rhombus. And a rhombus is a quadrilateral that all of its sides are equal to each other. And here all of its sides of rhombus APBQ indeed are equal to each other, and they equal to 5 units. So I will write it down. Quadrilateral APBQ is a rhombus that is to say all of its sides are equal to each other, and we will join points A and B together by a straight line. Actually, line segment AB is the diagonal of rhombus APBQ, and we will join points P and Q together by a straight line. PQ is also the diagonal of rhombus APBQ, and PQ equals to is the radius of this circle because of the fact that it starts from the center of the circle and ends at point Q, that is a point on this circle itself. Therefore PQ is the radius of this circle, that is to say PQ equals to 5 units because the radius of each circle equals to 5 units. And the diagonals of a rhombus has 2 characteristics. I will write them down. So I write down the two characteristics that a rhombus, the diagonals of a rhombus has. So the diagonals of a rhombus has two characteristics. First of all, the first characteristic of a diagonal of a rhombus is that they are perpendicular to each other. Okay? They are perpendicular to each other. So here, diagonal AB is perpendicular to diagonal PQ, and diagonal PQ is perpendicular to diagonal AB. That is to say, we have here four right angles. All four angles are right angles. We define the intersection point between diagonal AB and diagonal PQ as M. And the second characteristic of the diagonals of a circle is that they bisect each other. The diagonals of a rhombus bisect each other. Okay, so here the diagonal AB bisects diagonal PQ, that is to say PM equals to MQ, PM equals to MQ, and the diagonal PQ bisects diagonal AB, that is to say AM equals to MB, AM equals to MB. So we know that PM equals to MQ. So if we define PM as X, then MQ will be also equal to X, and X plus X is equal to PQ. X plus X equals to PQ. So X plus X is 2X, and 2X equals to PQ. But we have already found out that PQ equals to 5 units. PQ equals to 5 units. So from this equation, 2X equals to PQ equals to 5, we will derive that 2X equals to 5. So here we will divide this equation by 2, and we will get that X equals to 5 over 2 units. X equals to 5 over 2 units. So here we'll substitute X by 5 over 2 units. So PM that equals to X equals to 5 over 2 units, and MQ is equal also to X, and X equals to 5 over 2 units. So we'll substitute X by 5 over 2, 5 over 2, X equals to 5 over 2. In the next step, we will focus on triangle APM, triangle AQM, triangle BQM, and triangle PMB. So we focus on those 4 right triangles. I will write it down. We will focus on triangle APM. We will focus on the right triangle, triangle APM. We will focus also on the right triangle, triangle AMQ. We will focus on the right triangle, triangle PMB. And we will focus on the right triangle, triangle QMB. So actually, in these 4 right triangles, if we focus on angle APM, we'll focus also on angle MPB, we'll focus on angle MQB, and we'll focus on angle AQM. So on those 4 angles, we know that the cosine of those 4 angles, that I marked in this sign, the cosine of those 4 angles will be equal to 5 over 2 over 5. Here also it is 5 over 2 over 5. This angle, the cosine of this angle will be equal to 5 over 2 over 5, and the cosine of this angle in the right triangle, triangle AMQ, will be also equal to 5 over 2 over 5. So in all 4 triangles, the cosine of each angle that I marked here, it will be equal to 5 over 2 over 5. Again, the cosine of each of the 4 angles equals to 5 over 2 over 5. 5 over 2 over 5 is 5 over 5 times 2. 5 over 5 is 1, and 1, so it is 1 over 2. So in conclusion, we found out that the cosine of those 4 angles is equal to 1 over 2, and when a cosine of an angle is equal to 1 over 2, it means that the angle itself equals to 60 degrees. So the angle itself is equal to 60 degrees. That is to say, all 4 angles that I marked are equal to 60 degrees. So this angle APM equals to 60 degrees, angle BPM equals to 60 degrees, angle BQM is equal to 60 degrees, and angle MQA is also equals to 60 degrees. Okay? In the next step, we will prove that triangle APB is congruent to triangle AQB. Okay? So we'll focus on triangle APB. We'll focus on triangle APB. And triangle AQB. Okay, we'll focus on those 2 triangles and we'll prove that they can go into each other. So first of all, we know that AP equals to AQ equals to 5 units. AP equals to AQ equals to 5 units. AP equals to AQ equals to 5 units. And we also know that PB equals to BQ, and they are also equal to 5 units. So PB is equal to QB, and both sides are equal to 5 units. I'll repeat again. Side PB equals to side QB equals to 5 units. And side AB is equal to itself. Side AB is a common side. It belongs to both triangles. So we write down that AB equals to itself. AB equals to AB is a common side that belongs to both triangles. Okay, so AB equals to AB is a common side that belongs to both triangles. So actually we proved that triangle APB is congruent to triangle AQB according to side rule. I'll write it down. We actually proved that triangle APB is congruent, this is the sign of congruent, to triangle AQB according to side rule. Okay, all the sides of triangle APB congruent to all the sides of triangle AQB, therefore those two triangles congruent to each other according to side rule. And from the fact that those two triangles congruent to each other, we will conclude that they also have the same areas. So we will conclude that the area of triangle APB is equal to the area of triangle AQB. Okay, so I'll write it down. We will conclude from the fact that those two triangles congruent to each other that the area of triangle APB here actually the squared bracket is the sign for the area. It means the area of triangle APB is equal to the area of triangle AQB. Okay? And what is the area of sector APB? The area of sector APB the area of this sector, that is a shape that is very similar to a semicircle, but it is not a semicircle. So the area, no, but actually the area of sector APB, it is actually this shape APB is the triangle APB plus this semicircle. So the area of sector APB equals to pi r squared times 120 degrees over 360 degrees. So the area of sector APB equals to pi r squared times 60 plus 60 is 120 degrees, 120 degrees over 360 degrees. Okay? So, again, the area of sector APB is equal to pi r squared times 120 degrees over 360 degrees. And here, r equals to 5, so r squared is 5 squared. 5 squared is 25, so we have here in the numerator 25 pi over 120 degrees over 360 degrees is 1 over 3. So we found out that the area of sector APB is equal to 25 pi over 3 square units and what is the area of sector AQB? The area of this sector, sector AQB, the area of sector AQB will be equal to pi r squared times 60 degrees plus 60 degrees is 120 degrees over 360 degrees. So the area of sector AQB equals to pi r squared times 120 degrees over 360 degrees. Okay? And r equals to 5, so r squared is 5 squared. 5 squared is 25, so in the numerator we have 25 pi over 120 degrees over 360 degrees is 1 over 3. So it is actually the area of sector AQB also equals to 25 pi over 3 square units. So we can write down that the area of sector APB is equal to the area of sector AQB the area of sector APB is equal to the area of sector AQB and the area of both sectors is equal to 25 pi over 3 square units. And we also found out that the area of triangle APB is equal to the area of triangle AQB. And what is the area of segment APB? The area of segment APB the area of this segment APB is very similar to a semicircle, but it is not a semicircle, of course. So the area of segment APB will be equal to the area of sector AQB minus the area of triangle AQB. So the area of sector AQB minus the area of triangle AQB again, the area of segment APB equals to the area of sector AQB minus the area of triangle AQB. And we have already found out that the area of sector AQB equals to 25 pi over 3. And we will define the area of triangle APB that equals to the area of triangle AQB is x square units. So the area of triangle AQB is equal to x, so it is 25 pi over 3 minus x square units. That is the area of segment APB. And what is the area of segment AQB? The area of segment AQB the area of segment AQB, the area of this segment that is very similar to a semicircle, but it is not a semicircle. The area of segment AQB will be equal to the area of sector APB minus the area of triangle APB. So the area of segment APB minus the area of triangle APB is equal to the area of segment AQB, but we have already found out that the area of it's actually the area of segment AQB equals to the area of sector APB. Again, the area of segment AQB equals to the area of sector APB minus the area of triangle APB. And we have already found out that the area of sector APB is equal to 25 pi over 3 minus the area of triangle APB. The area of triangle APB equals to x. So in conclusion, we found out that the area of segment AQB also equals to 25 pi over 3 minus x square units, and it is exactly the same area of the area of segment APB. Therefore, we can conclude from those two equations that the area of segment APB equals to the area of segment AQB. I will write it down. So the area of segment AQB is equal to the area of segment APB. Okay? So, and what is the area of the green shape? The area of the green shape is equal to the area of segment APB plus the area of segment AQB. It equals to the area of segment APB plus the area of segment AQB but because of the fact that the area of segment APB equals to the area of segment AQB, we can substitute the area of segment AQB by the area of segment APB because they are equal to each other. So the area of the green shape will be equal to the area of segment APB plus the area of segment APB because of the fact that the area of segment AQB equals to the area of segment APB. Therefore, we will substitute the area of segment AQB by the area of segment APB. So here we found out that the area of the green shape equals to the area of segment APB plus the area of segment APB. That is to say, it equals to 2 times the area of segment APB. So we found out that the area of the green shape equals to 2 times the area of segment APB. Therefore, we'll calculate the area of segment APB, we will multiply it by 2, and we'll get the area that we are looking for, that is to say the area of the green shape. So the area of the green shape equals to 2 times the area of segment APB, and the area, we already found out that the area of segment APB equals to the area of sector AQB minus the area of segment APB. The area of segment APB equals to the area of sector APB minus the area of triangle APB. Again, the area of segment APB equals to the area of sector AQB minus the area of triangle AQB. That is to say, it equals to 25 pi over 3 minus x. So the area of the green shape equals to 2 times 25 pi over 3 minus x. So the only thing that we need to find out in order to find out the area of the green shape is it is actually the area of x, that is actually the area of triangle APB or the area of triangle AQB, because both the area of triangle APB and the area of triangle AQB, they are both defined as x, because they are equal to each other in their areas, and both they are defined as x. So we find out the area of triangle APB that is defined as x, and in this way we'll find out the area of the green shape. So the area of triangle APB, the area of triangle APB, this triangle, this is actually equals to x. Here it equals to the base of the triangle that is actually AB times the height that is actually PM over 2. Again, x equals to the area of triangle APB, and the area of triangle APB equals to the base of the triangle that is AB times the height to the base that is PM over 2. So we find out the length of AB. So here we know, we have already found out that AM equals to MB. AM equals to MB. So if we define AM as edge, then MB will be also equal to x, to edge. So if AM equals to edge, then MB also will be equal to edge because of the fact that they are equal to each other. AM equals to MB. So if we focus on the right triangle, triangle AMQ, in the right triangle, triangle AMQ, we know that sinus 60 degrees equals to edge over 5. I repeat again. In the right triangle, triangle AMQ, sinus 60 degrees equals to edge over 5. Sinus, so we'll multiply this equation by 5 and we'll get it 5 times sinus 60 degrees equals to h. Sinus 60 degrees equals to square root of 3 over 2. So it is 5 times square root of 3 over 2. So the value of h is 5 times square root of 3 over 2. So I write it down that h equals to 5 times square root of 3 over 2, and here also h equals to 5 times square root of 3 over 2. And AB equals to h plus h. AB equals to h plus h. H plus h is 2h, so AB equals to 2h, and we already found out that h equals to 5 times square root of 3 over 2, so 2h is 2 times 5 times square root of 3 over 2, 2 over 2 is 1, so in conclusion we found out that AB equals to 5 times square root of 3 units. Therefore, the area of triangle APB, that is actually equals to x, will be equal to AB. AB is 5 times square root of 3 times PM. PM equals to 5 over 2. All divided by 2. So here 5 times 5 is 25, and 25 times square root of 3 over 2 times 2. 2 times 2 is 4, so it is 25 times square root of 3 over 4. So x equals to the area of triangle APB, that equals to 25 times square root of 3 over 4 square units. And here the area of the green shape equals to 25 pi, 2 times 25 pi over 3 minus x. So it equals to 2 times 25 pi over 3 minus x. And we just right now found out that x equals to 25 times square root of 3 over 4. So here we will take 25 out of this expression as a common factor. So it will be equal to 2 times. So 25 is taken as a common factor. So what is left from 25 pi over 3 after we took from it 25 as a common factor? What is left? It is actually pi over 3. And what is left from minus square root of 3 over 4 after we took from it 25 as a common factor? What is left? It is actually square root of 3 over 4. So in conclusion, we found out that the area of the green shape equals to 2 times 25 is 50, so it is 50 times pi over 3 minus square root of 3 over 4 square units. I repeat again, we actually found out that the area of the green shape equals to 50 times pi over 3 minus square root of 3/4 square units. Okay? We finished with the first method. In the next step, I will present to you how to find out the area of this green shape according to the second method. So here we will define the center of this circle as point P. We define the center of this circle as point Q, as we did in the first method. We will define the first intersection point between those two circles as point A, and we will define the second intersection point of those two circles as point B. We will join together points P and B by a straight line. We join together points Q and B by a straight line. We join together points A and Q by a straight line. And we join together points A and P by a straight line. So here we already found out that all those line segments are equal to 5 units. They are the radiuses of those two circles. We will join points P and Q by a straight line. PQ also is equal to the radius of this circle, that is to say it equals to also 5 units. So triangle APQ is an equilateral triangle because of the fact that all of its sides are equal to each other. And triangle PBQ is also an equilateral triangle. And the equilateral triangle, triangle APQ, is congruent to the equilateral triangle, triangle PBQ. I will write it down. The equilateral triangle, triangle APQ is congruent to the equilateral triangle, triangle PBQ. According to side rule, okay. And from the fact that those two triangles congruent to each other, we will conclude that they have also the same areas. So the area of triangle APQ is equal to the area of triangle PBQ. Okay. And because of the fact that triangle PBQ is an equilateral triangle, all of its angles are equal to 60 degrees here. And because of the fact that triangle APQ is also an equilateral triangle, all of its angles are also equal to 60 degrees. Okay. So, what is the area of the green shape? The area of the green shape equals to the area of triangle APQ equals to the area of triangle APQ plus the area of triangle PBQ plus the area of the four segments, segment AP, segment PB, segment BQ, and segment AQ. Okay, I'll write it down. The area of those two triangles, the sum of the areas of those two triangles, plus the area of segment AP, plus the area of segment PP, segment PB, plus the area of segment BQ, plus the area of segment AQ. I'll repeat again. The area of the green shape equals to the area of triangle APQ plus the area of triangle PBQ plus the area of segment AP plus the area of segment PQ plus the area of segment PB plus the area of segment BQ plus the area of segment AQ. But because of the fact that the area of triangle APQ is equal to the area of triangle PBQ, we can substitute the area of triangle PBQ by the area of triangle APQ. We will do it now, and we will get that the area of the green shape equals to the area of triangle APQ plus the area of triangle APQ, because we substitute the area of triangle PBQ by the area of triangle APQ, so it is plus the area of triangle APQ again, plus the area of segment AP, plus the area of segment PB, plus the area of segment BQ, plus the area of segment AQ. So the area of triangle APQ plus the area of triangle APQ equals to 2 times the area of triangle APQ plus the area of segment AP plus the area of segment PB plus the area of segment BQ plus the area of segment AQ. So what is the area of triangle APQ? The area of triangle APQ triangle APQ here we will connect together points A and B by a straight line. We've already found out in the first method that here AM equals to MB, AM equals to MB, and we have already found out in the first method that AM equals to 5 times square root of 3 over 2, and it also equals to MB, that is also equals to 5 times square root of 3 over 2. So here the area of triangle APQ will be equals to the base of the triangle, that is actually PQ, times the height, that is AM, divided by 2. I will repeat again. The area of triangle APQ equals to the base of the triangle, that is PQ, times the height, that is AM, over 2. We already found out that PQ equals to 5 units. PQ equals to 5 units. AM equals to 5 times square root of 3 over 2. All divided by 2. So in conclusion, we found out that the area of triangle APQ equals to 5 times 5 is 25, times square root of 3 over 2 times 2 is 4. So the area of triangle APQ is equal to 25 times square root of 3 over 4, and 2 times the area of triangle APQ will be equal to 2 times 25 times square root of 3 over 4. Okay? Again, 2 times the area of triangle APQ equals to 2 times 25 times square root of 3 over 4, because the area of triangle APQ is 25 times square root of 3 over 4, so we will multiply it by 2 and we will get 2 times the area of triangle APQ. And what is the area of segment AP? The area of segment AP the area of segment AP equals to the area of sector AQP minus the area of triangle AQP. I'll repeat again. The area of segment AP equals to the area of sector AQP minus the area of triangle AQP. So, the area of sector AQP, this sector, equals to pi r squared times 60 degrees over 360 degrees. Pi r squared times 60 degrees over 360 degrees. R equals to 5, so r squared is 5 squared, 5 squared is 25, so in the numerator we have 25 pi, and 60 degrees over 360 degrees is 1 over 6, so the area of sector AQP equals to 25 pi over 6 square units, and we also have to subtract from it, from the area of sector AP, the area of triangle AQP. So what is the area of triangle AQP? We have already found out that the area of triangle AQP equals to 25 times square root of 3 over 4. So in conclusion, we found out that the area of segment AP is equal to 25 pi over 6 minus 25 times square root of 3 over 4. And what is the area of segment PB, the area of segment PB will be equal to the area of sector PQB minus the area of triangle PQB. I will repeat again. The area of segment PB will be equal to the area of sector PQB minus the area of triangle PQB. So here, the area of sector PQB, equals to pi r squared times 60 degrees over 360 degrees. And the area of triangle PQB, we've already found out that the area of triangle PQB is equal to the area of triangle APQ. And the area of triangle APQ is equal to 25 times square root of 3 over 4. So, in conclusion, the area of segment PB equals to pi r squared times 60 degrees over 360 degrees. R equals to 5, so r squared is 5 squared. 5 squared is 25, so it equals to 25 pi. 60 over 360 is 1 over 6, so it is 25 pi over 6 minus 25 square root of 3 over 4. So it is exactly equals to the area of segment AP. Okay, segment AP and segment PB have the same areas. So we can write down that the area of segment AP is equal to the area of segment PB. Okay, the area of segment AP equals to the area of segment PB. And if we continue to calculate the area of segment BQ and the area of segment AQ, we will find out that the area of those two segments will be also equal to the area of segment AP. Therefore, we will actually can calculate the area of triangle, we can multiply the area of segment AP by 4, and in this way we will get the areas of all 4 segments, segment AP, segment PB, segment BQ, and segment AQ in total. So 4 times the area of segment AP will be equal to the total sum of the areas of segment AP plus segment PB plus segment BQ plus segment AQ. So actually the area of the green shape, will be equal to 2 times the area of triangle APQ plus 4 times the area of segment AP. 4 times the area of segment AP. And we've already found out that 2 times the area of triangle APQ is equal to 2 times 25 times square root of 3 over 4 plus 4 times the area of segment AP, and the area of segment AP equals to 25 pi over 6 minus 25 square root of 3 over 4. Okay, so here we get that 2 times 25 is 50, so it is 50 times square root of 3 over 4, plus 4 times 25 is 100, so we'll get here 100 pi over 6, minus 4 times 25 is minus 100, so it is minus 100 square root of 3 over 4. So here we have 3 times square root of 3 over 4 minus 100 times square root of 3 over 4. It equals to minus 50 times square root of 3 over 4, and we also have to add to this expression 100 pi over 6. We'll divide both the numerator and the denominator by 2. 100 over 2 is 50, so in the numerator we will have 50 pi. 6 over 2 is 3. So in conclusion, we found out that the area of the green shape equals to 50 pi over 3 minus 50 times square root of 3 over 4. Here we will take out 50 as a common factor of those from those two expressions. So 50 is a common factor. So what is left from 50 pi over 3 after we took from it 50 as a common factor? What is left? It is actually pi over 3. And what is left for minus 50 times square root of 3 over 4 after we took from it 50 is a common factor? What is left? It is actually minus square root of 3 over 4. So in conclusion, we found out that the area of the green shape equals to 50 times pi over 3 minus square root of 3 over 4 square units, exactly as we found in the first method. The same results, we got the same results as we got in the first method. So in the next step, I will summarize the lecture. Actually, we wanted to find out the area of the green shape. We found the area of the green shape in 2 different methods. I will repeat on the question itself. We have here 2 circles. Each circle is passing through the center of the other circle, and we know that the radius of each circle is equal to 5 units, and we want to find out the area of this green shape. So, first of all, I presented to you the definition of a sector. The definition of a sector is the area that is bounded by 2 radiuses, and the arc that is included between those 2 radiuses is defined as a sector. So sector is part of a circle, and it is defined as the area that is bounded by 2 radiuses and the arc that is included between those 2 radiuses. So the green shape is sector AOB, and the area of sector AOB equals to pi r squared times 60 degrees over 360 degrees. But the general formula for the area of any sector is pi r squared times the radius between the two radiuses over 360 degrees. Again, r is the radius of the circle. Okay, so the general formula for the area of any circle is pi r squared times the angle that is between the two radiuses over 360 degrees. Okay, and I also presented to you the term segment. Segment is the area inside the circle that is bounded by the chord and by the arc that is attached to that chord. So here segment AB is the area that is bounded between chord AB and arc AB. Okay, again, segment AB is the area that is bounded by chord AB and arc AB. And the formula for the segment, the area of a segment is equal to the area of sector AOB minus the area of triangle AOB. You can see it easily that if you subtract from sector AOB the area of triangle AOB, you will get the sector AB. That is actually the area in the green shape. Okay, then we did constructions here. We joined together points. First of all, we define the center of this circle as point B. We define the center of this circle as point Q. We define the first intersection point between those two circles as point A, and we defined the second intersection point of those two circles as point B. And then we join together points B and Q, points B and P, points P and A, and points A and Q by a straight line. Each one of the line segments are the radius of any of those two circles. For example, PQ is the radius of this circle because of the fact that it starts from the center of the circle, that is to say from point Q, and ends at point B, that is the point on this circle itself. Therefore, BQ is defined as the radius of this circle, that is to say it equals to 5 units because the radius of each circle here equals to 5 units. The same thing is true for the other three line segments. They are also the radiuses of those circles. So by creating, by drawing those four line segments, we created here rhombus. Rhombus is a quadrilateral that all of its sides are equal to each other. Any quadrilateral that all of its sides are equal to each other could be a rhombus, not necessarily, but it also could be a square. A square is a quadrilateral with 4 right angles, but here any quadrilateral that doesn't have 4 right angles, but all of its sides are equal to each other, it will be a rhombus. Like in this example, APBQ is a rhombus. Why? Because all of its sides are equal to 5 units, they are equal to each other, and they are equal to 5 units. So quadrilateral APBQ is a rhombus, and we join together points A and B by a straight line. AB is the first diagonal of rhombus APBQ. We join together points P and Q by a straight line. PQ is also the second diagonal of rhombus APBQ. And the diagonals of a rhombus have two characteristics. Okay, the diagonals of a rhombus have two characteristics. The first characteristic of the diagonals of a rhombus is that they are perpendicular to each other. So here in rhombus APBQ, diagonal AB is perpendicular to diagonal PQ, and diagonal PQ is perpendicular to diagonal AB. That is to say, all the four angles here, 1, 2, 3, 4, are right angles. And the second characteristic of a rhombus is that they bisect each other. The diagonals of a rhombus bisect each other. That is to say, the diagonal AB bisect diagonal PQ. What does it mean? It means that PM equals to MQ. PM equals to MQ, and it is also true to say that the diagonal PQ bisects diagonal AB. That is to say, AM equals to MB. AM equals to MB. But we have already found out that PQ equals to 5 units. Why? Because it is the radius of this circle. It starts from the center of the circle, and that's at point Q, that is the point of the circle itself. Therefore, PQ is the radius of this circle. This is to say it equals to 5 units. And from one side, we know that PQ equals to 5 units. But from the other side, PQ equals also to PM plus MQ. And PM, if we define PM as X, then MQ will be also equal to X. So PQ equals to X plus X. PQ equals to X plus X, that is to say PQ equals to 2X from one side, but from the other side PQ equals to 5 units. From this equation we will derive that 2X equals to 5. We'll divide this equation by 2 and we'll get that X equals to 5 over 2. So X that equals to PM equals to 5 over 2 units, and X equals to MQ equals to 5 over 2 units. Okay? Then we actually focused on the right triangle APM, the right triangle AMQ, the right triangle PQM, and the right triangle PMB. On those 4 right triangles, if we focus on angle APM, angle BPM, angle BQM, and angle AQM, then the cosine of those 4 angles, equals to 5 over 2 over 5. Also here, the cosine of this angle equals to 5 over 2 over 5. The cosine of this angle equals to 5 over 2 over 5. And the cosine of this angle equals to 5 over 2 over 5. So in those 4 triangles, the cosine of the 4 angles that I mentioned, it equals to 5 over 2 over 5. And 5 over 2 over 5 is 1 over 2. And if cosine of any angle is equal to 1 over 2, it means that the angle itself equals to 60 degrees. Okay? And we found out that all 4 angles are here they are equal to, the cosine of them is equal to 1 over 2, therefore all the angles will be equal to 60 degrees. Why? Because of the fact that if any cosine of any angle is equals to 1 over 2, then the angle itself equals to 60 degrees, so all 4 angles will be equal to 60 degrees. Then we proved that those 2 right triangles, those 2 triangles can go into each other. Triangle APB can go into triangle AQB. Why those 2 triangles can go into each other? Because first of all, we know that AP equals to AQ equals to 5 units, AP equals to AQ equals to 5 units. We also know that PB equals to BQ equals to 5 units, and AB equals to itself. It is a common side that belongs to both triangles, so we proved that those 2 triangles can go into each other according to side rule. And from the fact that those 2 triangles can go into each other, we will conclude that they also have the same areas. That is to say, we will conclude that the area of triangle APB equals to the area of triangle AQB. Why? Because they can go into each other. Then we found out the area of sector APB. The area of sector APB equals to pi r squared times 60 degrees plus 60 degrees is 120 degrees over 360 degrees. So the area of sector APB equals to pi r squared times 120 degrees over 360 degrees. R equals to 5. R squared is 5 squared is 25. So in the numerator we have 25 pi. And 120 degrees over 360 degrees is 1 over 3. So in conclusion, we found out that the area of sector APB equals to 25 pi over 3 square units. Then we calculated the area of sector AQB. The area of this sector, the area of sector AQB will be equal to pi r squared times 120 degrees, because 60 plus 60 is 120 degrees. So it is pi r squared times 120 degrees over 360 degrees. R equals to 5, so r squared is 5 squared. 5 squared is 25. So in the numerator we have 25 pi. And in the denominator we have 120 degrees over 360 degrees is 1 over 3. So in the denominator we have 3. So in conclusion, we found out that the area of sector AQB equals also to 25 pi over 3, exactly as the area of sector APB. So we conclude from it that the area of sector APB equals to the area of sector AQB, and both areas they are equal to 25 pi over 3 square units. And we have also found out that the area of triangle APB is equal to the area of triangle AQB. So we define the area of those two triangles as x, and then we calculated the area of segment APB. What is the area of segment APB? It will be equal to the area of sector AQB minus the area of triangle AQB. Again, the area of segment APB equals to the area of sector AQB minus the area of triangle AQB. But we have already found out that the area of sector AQB equals to 25 pi over 3, and the area of triangle AQB equals to x. So in conclusion, we found out that the area of segment APB equals to 25 pi over 3 minus x per units. And then we calculated the area of segment AQB. What is the area of segment AQB? The area of segment AQB equals to the area of sector APB minus the area of triangle APB. The area of sector AQB equals to the area of segment AQB equals to the area of sector APB minus the area of triangle APB. And the area of sector AQB equals to 25 pi over 3, and the area of triangle APB equals to x. So in conclusion, we found out that the area of sector AQB also equals to 25 pi over 3 minus x square units. So we found out that the area of segment APB equals to the area of segment AQB. Okay? Again, the area of segment AQB equals to the area of segment APB. And what is the area of the green shape? The area of the green shape equals to the area of segment APB plus the area of segment AQB. The area of the green shape equals to the area of segment APB plus the area of segment AQB. But because of the fact that the area of segment AQB equals to the area of segment APB, we can substitute the area of segment AQB by the area of segment APB. We did it, and we got that the area of the green shape equals to the area of segment APB plus the area of segment APB. That is to say, it equals to 2 times the area of segment APB. Okay? So, what is the area of segment APB? We have already found out that the area of segment APB equals to 25 pi over 3 minus x, and we have to multiply the area of segment APB by 2, and we will get the area of the green shape. Okay? The only thing that is missing is x, and x is the area of triangle APB. Okay? And here the area, we have already found out that the area of triangle APB is equal to 25 times root of 3 over 4. So 25 pi over 3 minus x equals to 25 pi over 3 minus 25 square root of 3 over 4 multiplied by 2. So here we took 25 out as a common factor. So, and we got what is left from 25 pi over 3 after we took from it 25 as a common factor. What is left, it is actually pi over 3. And what is left from 25 times square root of 3 over 4 after we took from it 25 as a common factor, what is left, it is actually square root of 3 over 2. So in conclusion, we found out that the area of the green shape, equals to 50 times pi over 3 minus square root of 3 over 4 square units. Okay? We finished with the first method. Then I presented to you how to find out the area of the green shape according to the second method. In the second method, we did the same constructions as in the first method. We defined the center of this circle as point P, the center of this circle as point Q, the first intersection point as A, the second intersection point as B. Then we join together points A and P, points A and Q, points Q and B, and points B and P. We know that all those line segments are equal to 5 units. They are the radiuses of those circles. And we actually have here two equilateral triangles. Triangle APQ is an equilateral triangle. All of its sides are equal to each other. And triangle PBQ is also an equilateral triangle because all of its sides is equal to 5 units. So we can conclude that those two equilateral triangles can go into each other according to side rule, because all of their sides are equal to 5 units, and because of the fact that those two equilateral triangles can go into each other, we will conclude that they have also the same areas. So the area of triangle APQ will be equal to the area of triangle PBQ. Okay? And so what is the area of the green shape? The area of the green shape equals to the area of triangle APQ plus the area of triangle PBQ plus the area of the 4 segments AP, PB, BQ and AQ. Okay, the area of the green shape equals to the area of triangle APQ plus the area of triangle PBQ plus the area of segment AP plus the area of segment PB plus the area of segment PQ plus the area of segment AQ. But because of the fact that the area of triangle APQ is equal to the area of triangle PBQ, we can substitute the area of triangle PBQ by the area of triangle APQ. We did it, and we got that the area of the green shape equals to the area of triangle APQ plus the area of triangle APQ. That is to say, it equals to 2 times the area of triangle APQ plus the area of segment AP plus the area of segment PB plus the area of segment BQ plus the area of segment AQ. And what is the area of triangle APQ? The area of triangle APQ, this triangle equals to the base of the triangle that is PQ times the height that is AM over 2. Again, the area of triangle APQ equals to the base that is PQ times the height that is AM over 2. And here, PQ equals to 5 units, and we have already found out in the first method that AM equals to 5 times square root of 3 over 2, all divided by 2. So we got here that 5 times 5 is 25, so in the numerator we have 25 times square root of 3, and in the denominator we have 2 times 2, that is 4. So in conclusion, we found out that the area of triangle APQ equals to 25 times square root of 3 over 4. Okay, and then we calculated the area of segment AP. the area of segment AP equals to the area of sector AP minus the area of triangle A. The area of segment AP equals to, again, the area of segment AP equals to the area of sector AQP minus the area of triangle AQP. Again, the area of segment AP equals to the area of sector AQP minus the area of triangle AQP. And the area of segment AQP equals to pi r squared times 60 degrees over 360 degrees. And the area of triangle, so it is, and minus the area of triangle AQP, so pi r squared times 60 degrees over 360 degrees is 25 pi over 6, and the area of triangle AQP equals to 25 times square root of 3 over 4, so the area of segment AP in conclusion equals to 25 pi over 6 minus 25 times square root of 3 over 4. Again, the area of segment AP equals to 25 pi over 6 minus 25 times square root of 3 over 4. Then we calculated the area of segment PB. The area of segment PB will be equal to the area of sector PQB minus the area of triangle PQB. I repeat again, the area of segment PB equals to the area of sector PQB minus the area of triangle PQB. And the area of sector PQB equals to pi r squared times 60 degrees over 360 degrees minus the area of triangle PQB. But because of the fact that the area of triangle PQB equals to the area of triangle AQP, so the area of triangle PQB will be equal to 25 times square root of 3 over 4. So in conclusion, we found out that the area of segment PB also equals to 25 pi over 6 minus 25 times square root of 3 over 4, exactly as the area of segment AP. Therefore, we can conclude that the area of segment AP equals to the area of segment PB. So if we continue to calculate the area of segment PQ and the area of segment AQ, we will get that those areas also equal to the area of segment AP. Therefore, we can say that the total area of the four segments AP, PB, BQ, and AQ equals to 4 times the area of segment AP. Why? Because all the segments are equal to each other in their areas. So if we multiply the area of segment AP by 4, we will get the areas of those 4 segments in total. So we can write down that the area of the green shape equals to 2 times the area of triangle AQP plus 4 times the area of segment AP. And the area of triangle AQP equals to 25 times square root of 3 over 4. So we have to multiply it by 2. And we have already found out that the area of segment AP equals to 25 pi over 6 minus 25 square root of 3 over 4. So here 2 times 25 is 50, so we got here this expression equals to 50 times square root of 3 over 4. 4 times 25 is 100, so this expression equals to 100 pi over 6, and 4 times minus 25 is minus 100, so this expression equals to 100 times square root of 3 over 4. And here we have 50 times square root of 3 over 4 minus 100 square root of 3 over 4. It equals to minus 50 square root of 3 over 4. And here we divided both the numerator and the denominator of this expression by 2. 100 over 2 is 50. 6 over 2 is 3. So in conclusion, we found out that the area of the green shape equals to 50 pi over 3 minus 50 times square root of 3 over 4. Here we took 50 as a common factor of these two expressions. And inside the brackets, what is left from 50 pi over 3 after we took from it 50 as a common factor? What is left is pi over 3, and what is left from minus 50 times square root of 3 over 4 after we took from it minus 50 as a common factor? What is left? It is actually minus square root of 3 over 2. So in conclusion, we found out that the area of the green shape equals to 50 times pi over 3 minus square root of 3 over 4 square units, exactly as we found in the first method. Okay, thank you very much.